Okay, so I would like to present some of my applications about evaluation and identifying the ductile fracture area in the DWTT test specimen. My name is Pavel Skalny. I come from Czech Republic, from Technical University Ostrava. Currently, it's the oldest technical university in Czech Republic. So about my topic, so few words I will spend about my problem formulation, and then I will say some about fracture surface characterization. It will be done in two ways. I will use the fractal geometry concept, and I will use the normal vector characterization. Then it will be worked by two kind of algorithm. One is from cluster algorithm, the other is based on statistical or probabilistic approach, and then I will show some results about fracture identification. So since I'm not I'm not material engineer, so only some few words about my samples. So it's from DWTT test samples with following sizes. It was pre-notched with a notch about 5 millimeters depth, and the test was realized in a temperature of -20 degrees of centigrade. This is some example how looks the broken sample. We can see that there is some such as tongue of brittle fracture, and there is occurred the ductile fracture area, and there is presented the notch of the surface. So generally we can find some parts where we are sure where is ductile fracture and where is brittle fracture. But for example, in the center there can occur some part of ductile fracture. Okay. So motivation about realization, this kind of research. Very often after realization of the DWTT test, the expert evaluate the surface and say the ratio between the ductile and brittle fracture. Of course, is maybe the best way how to do it, but in other way it's loaded in some kind of human error. Sometimes it happens that two experts can get a little bit not the same opinion about the fracture ratio. So we try to use some informatic approach how to identify it. Okay, so I got 30 samples, and every was scanned about 30-60 values per square millimeter. So for one sample it was about 50,000 measurement. It wasn't in the great magnitude done, so it cannot be seen a lot from this kind of visualization. It looked that I have 50,000 values. Every value was in X, Y, Z value. In this way, look the top view of the scanned specimen. So you can see that there is really problem to see anything about the fracture. I think the main reason that the magnitude really is not sufficient, and the scan is loaded of some kind of error. But we will show that it's possible to proceed and to some way identify the fracture. Okay, so for describing the fracture surface, I will use the fractal dimension, fractal geometry concept, and new approach based on normal vector characteristics. So I think the fractal geometry concept is quite well known. To estimate the fractal dimension, I use maybe the most new way how to estimate is a box counting dimension. Okay, so some line of the fracture surface is covered with some kind of covering, and delta, it means it's absolute amount of the covered elements, and the delta is the diameter of the elements. I used, and I think it's most common to use the mesh grid, the square grid. So the delta is the length of a used square. Then it is used least square method for approximating the ds, the fractal dimension. Second approach, all the surface is covered by the net of triangle in this way that the edges, the vertices of the triangle corresponds to the real measurements. And then to every triangle it was calculated the unit normal vector, so that the vector perpendicular to the triangle. Then every normal vector was characterized by 5 values. Maybe the most best value for identifying the fracture surface is is the greatest angle phi of the normal vectors of neighboring triangles. So that I have a normal vector, and I find out the deviations of the neighboring normal vectors, and I choose this value where the angular deviation is the highest. It was took into account the x and y component of the normal vector. It was interesting that the z component didn't say nearly nothing about the fracture surface, so it wasn't used because of this fact. And then there were calculating the differences. We can say changes of x and y component when we compare it with the neighboring normal vector. So that the normal vector is characterized by 5 values, and it was placed in the center of gravity of the triangle. There are some values, so these are fractal dimension in the x direction, fractal dimension in the y direction, the angular deviation, and here are x and y components, and the differences. So those 4 values are presented in absolute values. Okay, so mostly we can say that there are some statistical significance, not on the xy component, but in other way we can say that, for example, the x in brittle fracture is significantly higher than in the ductile fracture area. Okay, it's not so great difference, but it's still statistically significant. Okay, and now I will speak about the identification. The reason why I compared it with the fractal geometry is why the fractal geometry is well known, and then I can expect, because there are many papers that take account the fractal geometry and compare it with some mechanical properties, so then I can expect that also the normal vector characteristics got some correlation with mechanical properties. Okay, 2 ways how to work just now only with the normal vector characteristics. One is a clustering algorithm K-means, and the second is usage of conditional probability. Okay, so just few words about the K-means algorithm. It's one kind of clustering algorithm. It's quite easy to implement, it's very fast, and okay, I start with initial centers. It can be chosen in many different ways, but very often it's chosen randomly, and then each observation is moved to the center where it is the nearest. Very often it's used the Euclidean distance, but any other are too possible to use. Then is calculating new centers, and the algorithm continues until there are no changes. We have no guarantee that our final results are the best. They are only best at the initial, depends on the initial centers, but still it works quite well, and it's good that it's very fast and it can be implemented parallelly, so it can be applied in a huge data set. Okay, the 2 examples. Here is a K-means cluster set applied, okay, where I choose the 2 clusters. So generally we can say that it roughly identify well the ductile and brittle fracture area. Still there are some inaccuracies. And here is example of 4 cluster. It looks better. We can see that the notch has its own cluster, the blue and the blue ones together, I think, corresponds to the brittle fracture area, and the yellow one generally corresponds to the ductile fracture. Still, there are some inaccuracies, for example, here in the area of high plastic deformation, but generally it works quite well. Another way, in a poor fracture area, it was determined the distribution of ductile fracture and brittle fracture, and then it was calculated the probability that every normal vector belongs to the ductile fracture, so that then the result is probability field and is presented here. So it works. We can see that it's the results are similar to the K-means, probably from 0 to 1. So this was the result, and some kind of conclusion. Maybe the most important note, I think, that the normal vector characteristics behaves as a sensitive parameter in fracture identification. Both K-means and probability values quite well corresponds to the real displacement of the fracture surface, and this kind of methods could be used to identify the fracture area. Compared to previous work where only maximum angular deviation were used, the multinomial characteristics prove much better. In the other way, there are some disadvantages about using the multinomial characteristics because it spends much more of computational time, and of course it can happen so that the K-mean can have sometimes problem with convert to some good solution, so then there's optional to start for a second time. Further research, we are thinking about to try some more complicated algorithms such as support vector machines. I saw already some results from hidden Markov field that worked quite well, and also the inspired bio-inspired image segmentation could be another interesting alternative for this topic. We already started to do some research and it works quite well. Okay, that's maybe all I wanted to say. Thank you for your attention.